Good evening, I am Jahnavi from group 957 and our project is DENOVO crystal generation from composition. I'll start by introducing our project and the research paper it's built on. Then I'll define the critical problem we are solving and I'll be showing the architecture which we have built. In material science, the arrangement of atoms, its crystal structure detects everything from how well a material conducts electricity to its overall strength. However, discovering new stable materials is incredibly difficult because atomic arrangements must follow strict physical laws and symmetric rules. Our goal is to use AI to bridge this gap and generate stable crystal structures directly from chemical composition. However, the base research paper describes that the traditional discovery methods like random search are slow and computationally expensive. Furthermore, existing machines learning models often fail because they don't capture the complex physical symmetrics required for a stable crystals. Our project is basically inspired by crystal diffusion variation autoencoder base paper, which is introduced a method to combine diffusion models with graph neural networks GNNS. This approach is revolutionary because it does not just guess structures, it uses a denoising process to gradually refine random atomic arrangements into stable physically valid forms. We are extending this work to build an efficient system for de novo crystal generation. Now, let us look at what our system actually does. In scope, we are focusing on AI based generation using crystal diffusion variation autoencoder model, learning from existing crystal databases and validating the structure we produce. Out of scope, we are not performing full quantum simulations like DFT or experimental lab synthesis at this work. Now let us look how basically our solution works. The system takes a chemical composition as input. It then utilizes the crystal diffusion variation autoencoder model which operates in two layers. First one diffusing model, second one GNNS graphic neural networks. Diffusion model basically converts random noises into organized automatic structures. GNNS ensures the relationship between atomic respects physical laws such as rotations and translations invariance. By the end of this process, the model output a predicted crystal materials that is realistic. This is the architecture model which we have built on de novo crystal generation from composition. In conclusion, the AI based approach significantly reduces our dependency on trial and error and expensive simulations. By learning the underlying patterns of known materials, we can discover new ones much faster than traditional methods allowed. By our next milestone, we will be demonstrating the crystal diffusion variation autoencoder model in action. We'll take specific chemical compositions, generate their crystal structures, and perform stability check to validate that these materials could actually exist in real world. Thank you for your attention. We believe that by combining the power of AI with fundamental laws of physics, we can accelerate the discovery of materials that will define the technology for tomorrow. Thank you.